Desmos, yeah. What looks familiar? From things we've done from beginning, from the first lesson to today.
There's the limits approaching.
We have a limit, right? We have a limit as x is approaching something, right? We have a function. We've seen that before, right? Tables, we've seen before. Graphs, we've seen before. That's all stuff we've seen before. Now, what is the one thing that's different that is going to be the basis of what we do today?
It's the graph on the far right.
No, we've seen graphs.
Oh, what?
We've seen graphs. What?
It never goes past 3 on the y-axis.
No, what about?
It doesn't end.
Yeah, what is x approaching? We're used to seeing an actual number there, right? An actual value there, right? We have as x is approaching positive infinity, and then we have as x is approaching negative infinity, right? That's the new part, okay? I'm not changing any rules about limits. Limits are still the same. They have not changed, but it's just now we're approaching infinity, right? Where is infinity on the x-axis? Way to the right we haven't even seen, right?
You're probably going to answer this question in the lesson, but why do they have a limit if it's just infinity?
Well, that's a great question. Why? How do we know what it's going to get to if we can't get to it? Yeah. We're looking for patterns, right? First example is great. This is the function here. So if we were doing limits like we did day one, we looked at a graph and found the limits, right? So if I was saying, what's the limit as x approaches positive infinity? Where would I go on my graph? Which way would I go on my graph? Right. To the right. I keep going to the right until I can't go any further, right? So let's do that. Let's see. So I would take it, I would start on the left and then go to the right. I'm going to positive infinity, right? Now I stop at 7, whatever, I don't know if this is probably 7 here. I stop there, right? I got a lot farther to go, right? I have a lot farther to go. But I can pretty much answer the question without going any farther. Why? Why do I know what y value is going to be down at the end of the rainbow at positive infinity? Well, what is the graph doing? Yeah. It's not growing anything, right? If I'm just looking at the y value here, it grows and grows, but then it stops growing, right? It stops growing. You can look at the table to prove it. If I were to plug in 1 into the original, I get 1.5. If I were to plug in 100, I get 2.9997. If I were to plug in 1,000, which way are these numbers going? To the right, towards infinity, right? It's going towards positive infinity, right? What is y doing? So it's getting pretty close to 3. Now, it's not going to get to 3. I know it says 3 here, but on Desmos, when I cut and pasted it, Desmos just rounds. So eventually, it was 2.99999, so many 9s that they're like, you know what, we're not going to write that, just give you 3. So it's not actually going to get to 3, but it's going to get so close that we're approaching that, right? So we would say the limit as x approaches infinity, what y value are we approaching? 3. 3. So these aren't necessarily 3s. I would say they're more approximately 3s. The wavy lines mean approximately. We're not getting to 3, but like I said, Desmos doesn't like to do 2.99. They stop writing 9s after a while. Okay. All right. Now let's go in the opposite direction as x approaches negative infinity. So which way are we going to go if we're approaching negative infinity? There you go, right? And what y value are we approaching as we go to the left? Same one, right? 3. You can look at the table to see, right? As we're getting smaller and smaller and smaller, as we go left, we get smaller numbers, right? Smaller numbers. Even though they're getting big, they're negative. Negatives mean small, okay? So the limit as x approaches infinity from the left is 3. Oops, not that side goes there, it goes over here. Okay? That's what we're going to be doing today. We're going to be using what we can to figure out where are we going at the end of the rainbow. We can't get to the end of the rainbow, right? I can't go to the right to get to infinity. I can't get there. But we can use patterns to see when it eventually gets there, what's the y value going to be? Just like we did there, right? Just like we did there. I'm noticing a pattern. It doesn't matter how many numbers I plug in afterwards, you're just going to get 3. Okay, eventually it's going to get to the 3. Okay, that's what we're doing today. That's what we're doing today. All right, so let's take a look at, so this idea of a horizontal asymptote. We know how to do vertical asymptotes. We talked about that last week. Okay, horizontal asymptotes are the same idea. They're just going in the different direction. They're going horizontally. So horizontal asymptote for this guy would be at 3. We say y equals 3. We would say horizontal asymptote at y equals 3. That means that graph will never cross that line. How do we know that? How do we know it'll never cross the line? That's what I'm going to talk about right now. When are there horizontal asymptotes? Because if there's a horizontal asymptote, you're going to find a limit. Okay? So the limits, we use 3 things. This is in words on the back. We're gonna write this out as a graphic organizer, but this is just in words, what it means. So if I have a rational expression, how do we know it's a rational expression? It's a fraction. If I got a fraction and I need to find the limit as x approaches positive infinity or negative infinity, just like we saw, there's going to be one of 3 options. Okay? If the degree of p is greater than the degree of q, so the degree is bigger on top. So real quick, I don't mean like angle degree. What does degree mean? Not the angles. I'm not talking about like 45-degree angle. If I say a degree of a function, what does that mean? Does anyone remember what that means?
Exponent?
Something about the exponent, yeah. It's the biggest exponent. The degree is the biggest exponent. Biggest exponent power. So when I say the degree, I mean if the biggest exponent power is on top, okay, we call it top heavy. Okay, we call it top heavy. Then the limit is either going to be positive infinity or negative infinity. That's your answer. Okay? If the degree for p and q are the same, equally balanced, the degree is the same, they match, then the limit is the leading coefficient of p and q. I'll give you examples on the back. Okay, I'll give you examples on the back. I just want to go over this on paper, on this first, and then we'll go to the back and give you some examples. If the degree on bottom is bigger, limit's 0. The limit is 0. Okay? So some of these, like if the degree is bigger on top, your answer is either going to be positive infinity or negative infinity. If the degree is on bottom, your answer is just 0. Move on. Okay? If it's in between, it's going to be a fraction. Okay, so let's flip it over to the back. I'm going to give you some examples here. Okay. This just says in math lingo what I just said. This just says in math lingo what I just said. If you want to find a horizontal asymptote, you got to check where the limit approaches infinity and where it approaches negative infinity. So as x approaches, if you have a limit as x approaches either positive or negative infinity, those go hand in hand with a horizontal asymptote. Okay? So if I need to find a horizontal asymptote, what I'm going to do is I'm going to do 2 things. If I need to find this, I'm going to find the limit as x approaches infinity, and I'm going to find the limit as x approaches negative infinity. If they're the same answer, I only have, then that's the answer. But sometimes they have different answers, so you got to check both. So they're going to ask us later, they're going to say, find the horizontal asymptote for this guy. How do we do it? We're going to do these two guys, okay? Okay, so if the degree of the numerator, top heavy, so this one's top heavy. If the degree on top is bigger than the degree on bottom, we call it top heavy. Okay? Let me move this top heavy here. The limit as x approaches either positive or negative infinity will always be either positive or negative infinity. And it will never have horizontal asymptotes. Okay? So if something is top heavy, your answer is either going to be positive infinity or negative infinity, the limit. And you don't have to worry about horizontal asymptotes because it won't have any. It will not have any. So let me give you an example of one. Let me give you an example. Here's a function. We have x cubed plus 2x over 2x squared minus 5. What is the degree of the numerator? So what's the biggest power of the numerator? 2 or 3. X cubed. What is the degree for the denominator? 2. Which degree is bigger, the top or the bottom?
Top.
So it's top heavy. So this one is top heavy. So it tells us a couple things. I'm not worried about the answer to the limit. It'll either be positive infinity or negative infinity, and we'll get to that later. But it will also have no horizontal asymptotes. Okay? All right, let me give you the opposite case. Bottom heavy. This is bottom heavy. Okay, if it's bottom heavy, the limit as x approaches either positive or negative infinity, either one, will always be 0. You will always have a limit as x approaches positive infinity or negative infinity where it'll be 0. That'll also be your asymptote, y equals 0. Your horizontal asymptote will always be y equals 0 for this case. This is a pretty mild one. When we get these, we like it because it's bottom heavy, the limit's going to be 0, the asymptote's going to be 0. Yeah, that's it. So if they ask us for the asymptote, the horizontal asymptote, 0, y equals 0. If they ask us for the limit as x approaches infinity or negative infinity, 0. Okay? What's another name for the y equals 0, the line? It's a horizontal line. What's another name for y equals 0? A more commonly used name. No? If I were to graph y equals 0 on a graph, Desmos or whatever graph, where would it be? It would be in the same spot as the? No, it's not a trick. It's just where would the graph be?
0.
So it would be at 0. What is 0?
Axis.
The x-axis. There we go. It would be the x-axis. It would be the x-axis. y equals 0. X axis. So what's the y-axis then? If I wanted to graph the y-axis, what would that be? X equals 0. X equals 0, yeah. Okay? Same thing, just different names. Okay, so let me give you an example. F of x equals 2x squared minus 5 over x cubed. It's supposed to be cubed. There we go. Plus 2x. Okay. So the degree on top is 2. The degree on bottom is 3. The degree on bottom is bigger, bottom heavy. So that means if I was finding the limit for this guy, it would just be 0. If I'm finding the limit as x approaches either positive or negative infinity, it would be 0. If I'm finding the horizontal asymptote, it would just be y equals 0 or the x-axis. Okay? The last example is equally balanced. Okay?
Before you move on, and
Yeah.
for the asymptote, or when the denominator is larger,
Yeah.
you said y equals 0, and then in parentheses after that, what's?
X-axis?
Oh, cool.
Yeah, it's just another name for it. So equally distributed. What if we have the same degree on top and bottom? What do? Well, the asymptote and the limit. So the horizontal asymptote and the limit as x approaches positive or negative infinity will be what's called a fraction of the leading coefficients. Okay. A fraction of the leading coefficients. So let me give you an example before we talk about what that means. So 3 minus 1x squared, or wait, let me not put 1x squared. 3 minus x squared, 5x squared plus 2x. Okay, there's our example. Okay, so fraction, we know what the word fraction means, right? Something over something, numerator, denominator, we know what that means. Leading, if someone is leading, where are they? In front. Coefficient, what is a coefficient? A number before a variable, right? That's it, you guys got it. A fraction of the leading number before a variable. So let's go to my example here. First of all, are they equally distributed? What's the power on top? What's the degree on top? What's the degree on bottom?
2.
So we get 2 and 2, right? Okay, so equally distributed. Okay. So now we're going to have, so if we were finding the limit, as x approaches either positive or negative infinity for f of x, right? For f of x. Either one, we would have to set up a fraction of the leading coefficients. Okay. So let's look at the top. What was the degree on top? 2. So just focus on that guy there. 2. What's the coefficient for x squared on top?
Negative 1.
-1, good, -1. So -1. I have a question. Why isn't 3 the leading coefficient? Isn't 3 in front?
That's the constant.
There you go, right? It's not really leading, right? It's not really leading because it's not the biggest power. Okay, so -1 is the leading on top. What's the leading coefficient on bottom? 5. 5. So when we get this, we only focus on the leading guys. So we said the leading coefficient on top was -1. The leading coefficient on bottom was 5. So what is the limit? -1/5. What is the horizontal asymptote? Y equals -1/5. So that one's not too bad either. Because it's just a fraction. You just fraction. If you can reduce the fraction, we can't reduce it, so you can't. But if you can reduce it, always reduce it. That's the only thing. Okay? That's it. This table will answer any question you have on your paper. So the better you can understand the table, you're going to be fine. The table is one of those things that when we take a test or a quiz, I would probably put on a note card so you don't have to memorize it. Okay? After doing it a while, it might become, you might remember it. If you do something long enough, you just automatically remember it. But this is one of the things that if I were taking the test for the first time, I'd probably put on a note card, okay, when we take a test or a quiz, okay? Okay, so let's look at number 1A. Yeah, go ahead. Let's look at number 1A. So it's a limit question. So my question, is it bottom heavy, top heavy, or equally distributed? We do this because it's approaching positive infinity. So I can't plug in positive infinity. How can I plug in a number that I don't know what it is, right? I know it's got a lot of zeros, but I don't know what it looks like. So we can't use our old rules by plugging in because I don't know what the number looks like. So that's why we use the table, okay? So is this one top heavy, bottom heavy, or equally distributed? Right? So I have some students say, whoa, what about the 5? We just look at this guy, right? But what about the 5? 5 isn't going to do anything. 5 is just 5. It doesn't change, right? Will x squared change? It's a variable. It'll change. So we just go, we get our sights on the part that changes, which is what you guys did. This guy here. So it's bottom heavy. Yep, I agree. It's bottom heavy. Okay? Okay. So we say bottom heavy. So bottom heavy says, what is the limit going to be? 0. So the limit as x approaches infinity for 5 minus 2 over x squared is 0. Next problem.
It's just 0.
Yeah, because they just wanted the limit. They didn't need horizontal asymptote. So we're done. Okay.
Which one would you say like the most common we're gonna see like throughout doing this stuff?
Oh, doing this stuff?
Yeah.
Probably equally distributed.
Okay.
Equally distributed is usually the one they throw in there the most. Now it's not heavy one way. They don't they don't give you like a bunch of this or not of this. But I would say over time, I would say equally distributed is probably the most common. But it's not like heavy on one side, you know what I mean? So yeah. Okay. All right, so we got one with an old friend, e to the x. 3 over e to the x. What does e to the x represent? I don't know. I don't care what number it is. I don't care. I just want to know what it represents. What is it? What type of function does it represent? If you're not sure, look on your, I believe it's on your reference on the back of the unit circle. I believe e to the x is on there or something close to it. Say it again? It's not natural log. You're close. Is e to the x on there? Pick one on there that's very close to it. Which is one that's very close to it? Looks familiar. Looks like it could be related to e to the x.
Oh, okay.
Say it, Christian. Say it louder. Exponential, right? The exponential one they give you, I think, is y equals 2 to the x. Is that the one they give you? What's the exponential one they give you? B to the x. B to the x. Yeah. So that means it could be any number. And on this case, it's just E. What is that graph doing? If you were going from left to right, what is it doing? If you were going from left to right, it's growing big time. It's exponential, right? Exponential are things that grow very, very fast.
That's why they use it in like economics.
There you go, right? They grow really, really fast. So knowing that, is this top heavy, bottom heavy, or equally distributed?
Top heavy.
So 3 is going to grow faster than e to the x? No, the opposite, right? This guy is going to grow a lot faster than 3. 3 is going to stay 3 forever. E to the x, as I plug in numbers, it's going to get bigger and bigger and bigger and bigger and bigger and bigger and bigger. So this one would be bottom heavy. Yeah. Exponential. Okay. So bottom heavy means the limit is 0. And that's it. So you're going to be doing a lot of this. And I'll stop right now for a second because I want to talk about the types of growth rates. Growth rates mean how fast things grow. So the top of the list grows the fastest. The bottom of the list grows the slowest. So factorials, you don't see them in here. If you see them in more in stats, factorials, you will never see a factorial in this class. So it does grow the fastest, but it's not something you have to worry about.
What's stats?
Statistics? Mm-hmm. Yeah. So in this class, the thing that grows the fastest are exponentials, and then polynomials, and then logs. Natural logs, regular logs, doesn't matter. And then after that is sine or cosine. And then the thing that grows the slowest, in fact, it doesn't grow at all, are constants. They just stay the same. 3 is a constant. That guy's not going to grow at all. It's going to be 3 till the end of time. This guy's going to grow fast because it's an exponential. Okay? So if you're not sure, go to the list. So when I say exponential, we talked about that, right? Anything with an exponent up top. Polynomial, what's a polynomial? You have 3 examples of polynomials right there. 1, 2, 3. Anything with x squared, x to the third, where the power is a number. Power is a number. Okay? It's the thing we look at most in this class. Logs, you guys know what a log is. If it just says the word log or ln, then it's a log. Sine and cosine. Think of the sine and cosine graphs. Do those grow?
They grow, but then they go back down.
Yeah, they do what we call oscillate. They go up, but then they come back down. And then they go up, and then they come back down. So do they grow? Yeah, but then they also decrease just as fast. So they oscillate. Anything that oscillates goes back and forth, back and forth. And then constants don't grow. Okay? All right, so let's look at 1C. We have a numerator, we have a denominator. Is it top heavy, bottom heavy, or equally distributed? Okay, so let's take a look at sine x. That's a sine, right? X. What power does x have? Just 1. So what type of function is just regular x to the first power? Is it...
The first power, it's not really.
Which of these? It's a polynomial, right? It's a polynomial. So now I'm going to ask you again, which one grows the fastest, the top or the bottom?
Wait, I don't know.
The bottom.
What?
The bottom.
The bottom's a polynomial. What's the top? So the top, anything up here grows faster than anything down here. So the bottom would grow faster. So it's bottom heavy. Okay, we've had a lot of bottom heavy. That's going to change right now. Top heavy, bottom heavy, equally distributed. Top heavy, right? The biggest power on top is 2. The biggest power on bottom is 1. Right? So this one is top heavy. Top heavy. Okay, so let's go back to our table and see what we said for top heavy, because I don't remember. So top heavy says you're either going to get an answer of positive infinity or negative infinity. Okay, so which one are we going to get? This is how you're going to tell. Okay, so let me rewrite the problem because I wrote on it a little bit. X approaches negative infinity. We get 3x squared plus x, and then I get x to the first minus 1. Okay. We know it's top heavy. So it's either, our answer is either going to be positive infinity or negative infinity, right? We said that. We got to figure out which one though. So this is where this is really the only time we use our previous knowledge of how to find a limit, right? We used to plug in, right? We always plugged in. So this one we have to whittle down, where is it going to be? Am I going to be at a really big positive number or am I going to be at a really big negative number? So what type of numbers is x approaching? So like -1? No. What type of numbers is x approaching? Well, where is x approaching? Negative infinity. So what type of numbers is x approaching? So like -1? If I said to you infinity and you told me 1, are those two numbers even close to each other? No, right? If I said infinity and you told me a number, what number would be closer to that than 1?
A lot of zeros.
Yeah, a million, a billion, a trillion, whatever's after that, right? That's what the numbers you would tell me, right? Okay, so now it's negative infinity. So what type of numbers would you tell me if for negative infinity? Negative a bajillion, right? The biggest number you can think of. An extremely big negative number. Okay, think that in your head. Negative big, negative big. Okay, so if I was to plug in a negative big up top for x, I'm only worried about the big dogs. I'm not worried about the little ones. So this guy, so I'm going to focus in just on here. Because they're the ones that told me it was top heavy. So if I was to plug in a very, very big negative here and here, what type of answer, positive or negative, would I get? So if I plugged it in on top, that number that you had in your head, if I plugged it in on top, would I get a positive number or a negative number?
A negative number.
Why positive? Because it's squared, right? If I square a number, doesn't it become positive if it wasn't positive before? Okay. On bottom, would it become positive or negative? Because he didn't do anything to it, right? So it would stay negative. And what is a positive divided by a negative?
Negative.
So it's negative infinity, yep. A lot of mental math.
So there's not much, like, as much of the whole algebra, just crunching out numbers.
Not on these, because you can't really plug in a number because it's infinity.
It's just like finding the pattern.
It's just, yeah, it's a lot of mental math. For this guy, it's a lot of using the table and mental math, yeah.
And then also, oh, sorry, Travis, you go first.
Weren't there some infinities that are bigger than numbers?
Theoretically, I just say pick the biggest number you can think of. What's the biggest number you would like to have in your bank account? And then go from there. That's usually what I say. Because yeah, you could. Like you could say a gajillion million, blah, 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 but then there could always be a bigger number, right? So just pick a big number, whatever is big to you. I usually pick a billion or a trillion. So whatever is big to you. That's great. Yeah, I don't even know how many zeros it has, but yeah. What's up,
And
Christian?
also with like limits and stuff,
Mm-hmm.
like I was wondering this doing the homework over the weekend, but like where like in the real world do like people like
Limits themselves?
or like how are they used in like with other things?
So that's a great question. Not so much limits, but a lot of derivatives. When we talked about derivatives, it'll be, I got to think about where you see limits, like in the real
So
world.
it's just like another tool in your tool belt kind
Yeah, because it's what we're doing right now is we're building blocks so that when we get to derivatives, it's kind of like we're building foundations. So you don't really use the foundations, but when we get to derivatives, there's a lot of applications for derivatives. Yeah. Yeah. Yeah, go for it. All right, letter E now. Letter E. Let's flip it over and take a look at letter E.
Is there such thing as a polygon with sides or points?
Probably. What it looks like, I have no idea, but probably.
Because if I had that and then applied it to the theorem I was talking about, this, pretty sure I would still get 2.
Okay, so here we go. Positive, so we have 3 options. It says infinity. So it says infinity, so that means we got to go back to the table. We have top heavy, bottom heavy, equally distributed. So which one do you think this one's going to be? It's kind of a trick question, kind of a trick.
The equal one?
It's going to be equal. It's actually going to be equal. It's actually going to be equal. Yeah, why? I see a 2 down here, and I see a 1 up here. So why equal?
Well, because it's square rooted.
Yeah. What does square root mean? It means you're taking away, you're halving the power, right? So yeah, this one's kind of in disguise. So this one actually is a equally distributed, okay? Because the top is 1x to the first power, right? The bottom is the same thing. It really is the same thing because, and remember, we only focused on most important parts. 4 is not important to this problem. Sorry. So we get equally distributed. All right, so what did the table say when it's equally distributed? Fraction of leading coefficients. So let's go to our leading coefficients.
That's a terrible joke.
What does the table say about this problem? So what's the leading coefficients for this guy? 1 over 1. So your answer is 1. Because wasn't it 1x to the first, right? And then the square root of 1x squared, right? So the square root of 1x squared would just be 1x to the first, right?
I forgot that we don't include the 4.
Yeah, the 4 doesn't. So for these, only the degrees are the ones that really matter.
So technically, you add it back into 1.
Yeah,
When it was 1.
Say again?
Couldn't you add 4 back in?
We don't need it because 4 is just 4. It's not gonna. We only the degrees are actually going to have consequence because right now, if I were to plug in 1 or 2 or 3 to this guy, yeah, 4 is going to make a difference. But think of a number so big, that number in your head, right? So big. If I add 4 to it, is it going to do anything to the number? If I have $1 trillion in my bank account, and then someone gives me $4 and I put that in my bank account, is that really going to make a difference? No, 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 right? If you have $1 trillion in your bank account, I will give you $4 and it won't touch a thing, right? It won't touch a thing, right? That's the idea of why is 4 not important to this problem? Because we're dealing with very big numbers or very small numbers, okay? That's why. Okay, here we go. Top heavy, bottom heavy, equally distributed. Good. What is the degree on top? 3. What is the degree on bottom? 3. We knew that already, right? So we're going to focus in on those guys. We're going to focus in on just those. The 7 and the 1, again, that's like adding pennies to your bank account that's got millions and billions and trillions of dollars. So we got negative 3x3 and we got positive 2x3. What is a fraction of the leading coefficients? Negative 3 over 2. Good. That's the limit.
I mean, everything else would cancel out.
Okay. Okay, so let's look at G now.
Oh, I'm excited now.
What was it you wanted for your funeral?
It was like the
Those little white flowers.
All right. Okay, so for G, we have a lot of things that haven't been simplified, right? Shouldn't the top, you have done distributive property, and on the bottom, we should have done FOIL. We should have done that, right? Well, we're not going to do that right now because I don't care about all of it. I just care about the big powers. So if I was to actually do distributive property, what would the biggest power be? 2. Still be 2, right? What would be the number in front of the x squared? 12. Because 4 times 3 would be 12, right?
Yeah.
4 times -2 would be -8. But again, if you had $1 trillion in your bank account and I said, give me $8, that's nothing. It's not going to touch. It's not going to, in the long scheme of things, it's not going to do anything to it, right? Okay. Now the bottom, if we were to FOIL, first, outer, inner, last. So if we were to go this times this, this times this, this times this, this times this, which would produce the biggest power?
The 4x cubed and the 2x.
There you go. The 4. So what would we get when we got that?
5, right?
X5, yeah. What would the number in front be?
My bad. 8.
8x5, right? Yep. This guy here would produce the biggest. This guy here would produce, if I multiplied those two guys, would produce the biggest power. So those are the ones I'm focused on. Everything else, I could care less about. Top heavy, bottom heavy, equally distributed. Bottom heavy, I agree. So let's go to our table. What does our table say when things are bottom heavy? This limit is 0, right? So 0. Okay, do H. I want you to do H right now. Do H on your own.
Oh, okay. Well, let's see. Let's get out this little one more then.
Let me come back. He's gonna do the round. Just watch. What's the square root? 2 plus 5. What happens when you square root of 6 now? 4 probably. Wouldn't it be a 4 because the square root gets rid of it? Definitely not. It becomes 3. How does it become 3?
Wait, I'm so lost.
That's not how it works.
Then how does it work?
I don't know, but that doesn't sound right.
No, I don't know. All I know is that the square root of 6 is smaller than
I
6.
think it cancels out the actual square, but
Oh, are you sure the square root of
it's sort of like saying,
no, wouldn't it be equal because when it comes to exponents, you are just like subtracting and adding the
Okay, no, that's
exponents.
not.
Getting
Square
rid of
isn't the
the
square.
square rooting it. The power is 6, wouldn't it just be 4? Because 6 minus 2 is 4? Yeah, I'll fucking know. What are you talking? Wait, no. It's not, there's nothing you can do to the
Okay, so
top.
the 2 turns into a 1, with the 6 turns into a 5, and 3
Bigger
turns
than
into
the
2.
bottom,
Or just like not affected.
but equal.
The square
It would
root
just
is not
subtract the x, so it's
The square root of 6 is smaller than 4. That's all that matters.
Okay.
What?
So the top square, the power is the biggest is 6, but it's got a square root with it, right? So 64x6. The bottom is 7x4. Those are the biggest powers, right? The rest of it, I don't care about. I'm just focusing on the powers. Okay, so I need to simplify first. Before I do bottom heavy, top heavy, equally distributed, I have to simplify. All right? So what's the square root of 64? 8. If I take the square root of x to the 6, what is the power going to be?
4.
So what do you always do? What did we do for this guy? What did we do to the power? Halved it. That's what you do. You half it. You half it. 3. Because remember, you add the powers, and then this one stays 7x to the 4, right? It was bottom heavy. Okay? So our table says if it's bottom heavy, it's going to be 0. Okay. So at first, this is going to seem very weird, maybe not natural, but as you do it more, you'll get more and more used to it, okay? Okay, so the last example, the last set, is now we have to do both. We have to do horizontal asymptote and I have to do a limit. They go together. Luckily, they go together, so it's not like you're doing two different things. They go together, but we just have to do both. Okay? So the limit as x approaches positive infinity. So what does that tell us? Bottom heavy. I agree, it's bottom heavy. So what is the limit going to be? 0. What is the horizontal asymptote going to be? Y equals 0. Yeah, y equals 0 because it's a line. Don't just put 0. We want the equation of the line. Okay. 2b. Bottom heavy, top heavy, equally distributed. Equally distributed. So what do we got? What are the big dogs? 2x2 and 1x2, right? So equally distributed means a fraction of the leading coefficients, right? So the leading coefficient is 2, positive 2 over positive 1, which is just positive 2. Okay? So we get horizontal asymptote at y equals 2. Here's the thing, though. One thing before we go on. There's a reason I wrote this up here 30 minutes ago. To find horizontal asymptotes, you have to not only, we just did this, right? Didn't we do positive infinity? But you also have to take into account negative infinity too. Okay, if they're the same number, great. It might not be the same number.
I thought when the, oh, my bad.
Yeah.
I thought this was the top heavy one, my bad.
Oh, okay. Question you might have in your head, why didn't we do that for the first one? Why did I just say y equals 0 and move on? Because 0 is 0. 0, it's just 0, okay? If you get 0, it's not going to be anything, okay? That's the only option. What's that?
How'd you get 2?
2 divided by what? Up there? Okay, yeah.
So wait, how would it be different from positive infinity to negative?
We're going to see, it might not. I'm going to show you how to check them. So now let's redo the problem, except now we're doing negative infinity for the same problem. Now I'm not going to rewrite everything out. I'm just going to rewrite the big dogs that I had before. It's still equally distributed, right? But if I was to plug in a very, 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 very big negative in for x here, would I get a positive number or a negative number? Positive, right? How about if I did that to the bottom? Positive. I get positive, right? I get a positive answer. Is my answer positive? So I'm okay. Let's say you would have got a negative. That means your other one would have been negative 2. So it's just the sign that's going to change.
So there would be 2 horizontal?
Yeah, there would be 2 horizontal asymptotes, yeah. Yeah, so because I got a positive and the one I already have is positive, we're good. That's it. 1 horizontal asymptote, positive 2, move on. If you would have got a negative here, that means you would have had another one at negative 2. That's why we didn't have to check 0, because positive 0 and negative 0 are the same thing. Okay. All right, let's go to the letter C. Last one. This will be the last one we do today, and then we'll finish tomorrow, and then you guys can work on the practice. Yeah, we only got one problem after this. Okay, so here we go. Bottom heavy, top heavy, equally distributed. Top heavy, right? So let's go back to our paper. What happens when we have top, or a table, what happens if we have top heavy? It's either going to be positive infinity or negative infinity, right? It's either going to be one or the other, right? How do we figure that out? Well, isolate the big boys. Actually, no, let's do it like this. Watch. X to the fourth plus x cubed plus 9. So I'm going to rewrite it except no x's. And I want to know, will I get a positive answer or a negative answer? So again, that negative big number you were thinking about in your head, if I was to plug it into the top, would it be positive or negative answer? So let's start here. If I was to plug in a negative number here, would it be positive? It would be positive, right? Because fourth power means positive. This number would be negative, right? But wouldn't this number be a lot bigger? So wouldn't it cancel it out? So you're still positive, right? And then I add 9, that's positive. Okay, let's do that to the bottom now. That big number you have, that negative big number, if I multiply it times 3, would it be positive or negative?
Negative.
And then I subtract 3, it's still going to be negative, right? So when you divide a positive by a negative, what do you get? So that means our answer is going to be negative infinity. What about horizontal asymptotes, though? What did it say about horizontal asymptotes? There's none. No horizontal asymptotes. We don't even got to check. Okay? We'll leave e to the x for tomorrow. I know you guys can't wait. So we'll take about 5 or 10 minutes to finish this, and then I'll give you the rest of the time to do practice 4. And if you have questions on practice 3 or practice 2, I can help you too. Okay? Just getting used to it. Practice. More and more. The more practice you have, the easier it never becomes easy.